Let us now take a closer look at identifiability. As we said before, identifiability means that we can determine a unique solution for our optimization problem. So we find a solution and there is only one. Identifiability will depend on several parts. So it will depend on the model structure. In what way are the parameters incorporated in the model? It will depend on the choice of the parameters. So depending on the parameters that we choose to estimate, a model can become identifiable or not. So it also varies with the different choices of the parameters that we take. And it will depend on the data that we have. Because we use the data to estimate our parameters, we have to have data with sufficient quality and sufficient quantity. So there has to be sufficient information in our data set that we can uniquely define, uniquely determine a solution. So if we can give a unique solution for our optimization problem, assuming that the model is correct, so assuming here that, if we can find a unique solution, assuming that we have perfect data set, then we say there is structural identifiability. So if we say, basically, if I would collect all data perfectly for an infinitely large data set, and then I can find a unique solution, then I say it is identifiable, it is structurally identifiable. When do we say it's not identifiable? Well, if there is more than one solution, and usually this is linked to correlation. So similar as before, what we saw with the correlation in linear regression, also here, if there is correlation between different parameters in my model, this will give us problems because it will not have a unique solution. So we have multiple solutions, multiple possible solutions, and we cannot say one is better than the other. So if we still estimate, in the case of correlation, if we still estimate the parameters, it means that we have this dependence, and as such, the accuracy of the estimations, the accuracy of the estimates also becomes smaller. So we have low quality estimators, and usually often they are not even unique. So of course we cannot get perfect data. We never have an infinitely large data set with all variables measured and so on and so on. So it can happen that although the model is structurally identifiable, we cannot find a unique solution because our data quality is not good or our data quantity is not good. And in that case, we call that, or we say that the model is practically unidentifiable. So there's a difference between structural unidentifiability, where it's due to the model, and then practical identifiability, where it's due to the data, which are not good enough. Identifiability can be verified using identifiability analysis, but it's outside the scope of this course, and so we will not go further into detail for that. Let's take a look at two very simple examples. So model 1, we have y is ax1 plus bx2, and we want to minimize this model. So in this case, we have basically two unknowns, a and b, where we have to find optimal values. How do we do it? We derive to the variables. In this case, we have two variables. So on the one hand, you get delta y, delta x1, which is a. On the other hand, you get delta y, delta x2, which is b, which we then have to set equal to 0 for finding a minimum. But we see that we have two equations for two unknowns. So in this case, we get a unique solution. Unique solution, so there is identifiability, given that the data are sufficient. But in this case, we can solve it analytically. So we can see that we have a solution using the model itself. So structural identifiability, two equations, two unknowns, we find a unique solution. If on the other hand, there would be a dependence between x1 and x2, so let's assume x1 is alpha times x2, then this becomes a problem, because then the solution is no longer unique for the data that we have. So based on the model itself, we could find a solution, a unique solution. So that's a structural identifiability, assuming that we have the data. If my data are correlated in this case, it changes. So my model changes basically to y is a alpha x2 plus b x2. And so we see now that we are confronted with two unknowns, a and b, but we have only one variable remaining. So there's only one equation to solve two unknowns. So in this case, we cannot find a unique solution, and so it's not practically identifiable because my data are correlated. Second example, model 2, y is ax1 plus bx2 plus c times x1 plus x2. In this case, we have three unknowns, a, b, and c, but we only have two variables, so we can only derive y to x1 and y to x2. So we get basically three unknowns, but only two equations to determine these unknowns. So we can never ever find a unique solution. Even with perfect data, it's impossible to find a unique solution for this model. So in this case, it is not structurally identifiable. So just as before, we will use the residuals to check the assumptions of the model. And the properties of the residual are a function of the model structure on the one hand and the data that we have on the other hand. So what we said before is we assume that the model is correct. So basically, there is no error in the model structure. We assume that mathematically this model is the correct model. And so if there is any measure, or if there are residuals, if there is a change between the prediction and the observation, this is due to measurement errors. It's always due to the variation in the data. And so we say residuals will be due to the measurement errors in this case. So residuals, just to recall, we would write them as yi minus y hat I theta, and it's going up again. Basically, a residual, this is a part which is not explained by the model. So it was left over after we have applied our model. So it's the part of the data which are not explained through the model. And so it also bears information on the model quality. Because if the residuals still show a trend, they still show some pattern, it means that the model was not sufficiently or not sufficiently good, because then we could have found a better model to remove the pattern. So it carries information on the model quality, and so sometimes also selection criteria for the model are based on residual analysis. If we now look at residuals, so we have on the one hand state variables, usually time. If the state variable, well, in this case, we will call it a time series. So we look at what happens over time, which is a very common model that we are looking. We want to see what happens with something over time. So we will always assume that the errors in the state variables are negligent with respect to those of the dependent variable. So there are either no errors in the state variables, or they are so small that we can ignore them. And so the errors, the measurement errors, they will only depend on the dependent variable y. What we assume again here is that my errors, my epsilon I, are normally distributed, have a mean of 0, they have a constant variation, constant variance, sigma squared, and they are independent. So epsilon I is 1 to capital N, are independent. So there is no structure, there is no dependency between the different residuals. To check homoscedasticity or heteroscedasticity, we do the same as with regression. We make a residual plot. Only now for time series we will plot in function of time. So on the y-axis we get the residual, the error. On the x-axis we get the time. And what we want is, again, it has to be a constant variance over time. So what we want is that here the band around the central line is approximately constant. So it's a nice band with parallel lines. There's no increase, no decrease. On the left hand, so we see homoscedasticity. On the right hand, we see that it is increasing over time. And so there is heteroscedasticity. The variances are smaller in the beginning and they increase when time goes by. To check for independence, we will do the same or something similar as we did with correlation. So correlation checked the dependency between two variables. Now we don't want to check dependency between two variables, but we want to check the dependency between two residuals which differ a certain amount in time. So what we do is we study the autocorrelation with lag tau. Autocorrelation here basically checks the correlation between the same variable, but at different time points. So instead of having two different variables, we now have one variable, in our case the residuals, and we see if we have a certain amount of time between those two variables, are they correlated, yes or no? So if you recall the correlation, the definition of correlation between x and y, I will give you the sample correlation, was the sum of xi minus x bar, so minus its mean, yi minus y bar, and then we divide it by n minus 1 times, sx and sy. So the standard deviation for x and the standard deviation for y. The autocorrelation, what it does, it looks at, in our case, the residuals. So it checks for a residual and a residual at a different time point. The time point, or the difference between time points, is what we call the lag. We denote with tau. So in our case, this corresponds to the x. So it's the residual at a certain time. And then the y is the residual, but at a time tau later. So it's the same, or you start from a time point and then you add tau in time and you check those two. We have x bar, or in this case epsilon bar, is 0 because we assume that the average of all the residuals is 0. So that's why we get epsilon minus 0 times epsilon minus 0. And then this one plays the role of the variation. So this one corresponds to, so this is a normalization factor, which is something similar as the Sx times Sy in the correlation formula. In this case, the variance of epsilon was sigma squared. So here we have Sx and Sy being equal to sigma, and this is incorporated in this normalization factor. And so what we basically do is we have, if we look at the time points, so time point 1, 2, 3, 4, 5, 6, and we say, for example, my tau is 2, so my lag is 2. What I do is I compare 1 with 3, then I compare 2 with 4, then I compare 3 with 5, 4 with 6, and so on, and so on, and so on. And I do this over all time points that I observed. This allows me to see how they are correlated, so how there is a correlation between a residual now and the residual further in time. Of course, we want that this correlation is small, because we want that there is no pattern, that there is no dependency between the residuals. So we want the autocorrelation, also called the serial correlation, we want it to be small. And so what we see here, if we plot this, the first one is just a residual plot, or an example of a residual plot. You plot all the residuals over time. The second one here, this gives me the autocorrelations for the different time, for the different legs. So on the x-axis you see there is tau, so it's for the different legs. And then on the y-axis you see that there is normalized covariance, or basically the correlation, or in this case autocorrelation. What do we see? We see that the correlation the lag move from 0 to 20 in this case. The first one, the 0, so this bar, what we note is that it's 1, which is basically logical because it compares a point to itself, so there is no lag, so tau is 0. So what you do is you compare epsilon t with epsilon t. So it's the same variable, there is no difference. And so it's logical that the correlation is 1 because they are perfectly correlated. It is the variable itself. So the first bar will always be 1. So for leg 0 you will always get 1. And so you can ignore this one in the plot. You don't have to mind it because it doesn't give you any information. Then the second one is for tau equal 1. So this one checks epsilon t versus epsilon t plus 1 over all time points that we have. Tau is 2, checks epsilon t versus epsilon t plus 2, and so on, and so on, and so on. And so we make these correlations, and as we said, we want them to be small. So the question is now, how small do we want it to be? So what we will be doing is we will compare it to a cutoff value. We know, or we can prove, that the correlations under ideal assumptions should have a normal distribution with average 0, and 1 over n variance. So what we will be doing is we will check this with the quantile from a standard normal. So check values versus quantile of normal distribution. So if we want to have a 95% significance level, or confidence level, what we do is you look at the quantile, which you know is 1.96, and then you multiply with the sigma, the variance. So this is this is the same reasoning as in confidence intervals. Confidence interval, you had the average plus or minus the quantile times the standard deviation. In this case, the average is 0 plus or minus 1.96 for a 95% significance level times sigma. So sigma is 1 over square root of n. So it's 1.96 divided by square root of n. And so this is our cutoff value. So plus and minus. So we have a positive one and a negative one. And what we then want is basically that 95% of my autocorrelations lies within this interval. Here, what we see is there are 1, 2, 3, 4 which lie outside the interval. And so 4 out of 20 is 20%. But we would allow only 5% to lie outside the interval because it is a 95% confidence interval, or something similar to a 95% confidence interval. And so here 20% lies outside instead of 5. So there is a dependence between the different residuals. The autocorrelations, there are too many large autocorrelations, and so the residuals in this case are not independent. Solution for this, which is a bit archaic, is to subsample. Subsample is basically keeping only part of the data. So you keep part of the data. And so basically a rule of thumb, if you have 4 significant legs, you keep 1 out of 5 data points. So you keep the first, then the next 4 you don't keep, you throw them away. The sixth one you keep, then 4 you don't keep, you keep, 4 you don't keep, and so on. It's a very simple solution, but it's not an ideal solution. And it's, well, basically people are coming back from this technique and are avoiding against using this and look for better solutions.